Okay, so this video is for particularly for people who could not follow the small signal analysis which we did today, right? So I think one of the messages that if you are not able to follow, please speak up because we can delve into it these details there itself, right? From the next classes. So the question is that when we linearize the MOSFET characteristic, what is as a result? What we did is that okay, if it is a NMOS, right, which is having these three terminals, right? Drain source and body is we are assuming that the body is shorted to source in this, right? So that does not play much of the part. And in the gate drain source, what you see, if you were to linearize the characteristic, you could make a small signal model of this. This is what we saw in the previous video of MOSFET in saturation, right? This is the result of the linearization, which we have seen using Taylor series. So now when we do that, what we can do, we can see clearly that now the drain to source, we have a current source, a voltage dependent current source, right? So this is your gate, this is your drain, this is a source, right? Between gate and source, we are applying the small signal, which is GM small VGS. And between then drain and source, we have a response of it, which is given as small GM, small VGS, right? Which is the perturbation this is causing. And another perturbation which we saw was coming because of the drain source voltage, so which is VDS, right? This small voltage, which is also equal to V naught. This is also equal to Vn, right? Now, the another part which we saw that because of the output voltage of GDS, there was another component which come in, which we can represent either as a resistance, right? Where the resistance itself of this term becomes equal to V out divided by R naught. That is the current which is flowing into this, right? Or we could represent this as a current source also, right? Which is GDS. We saw GDS into VDS. This was another way, or this term can be represented, or this current is R naught. Whatever you're comfortable with, you can put is R naught, which is equal to anyway R naught. We know R naught is equal to 1 by GDS, right? So if you're comfortable with this convention, you can put it in this convention. That is okay. So this is the small signal model of this MOSFET, right? If we apply this small signal model, the only thing which we have here is this RD, which is also connected to drain, right? That is the part which is connected to drain, this RD. And where is it connected to? VDD. But we know now that in small signal analysis, because it's a incremental analysis, there is no perturbation to VDD, right? If we assume no perturbation to VDD, then what we can do is we can short VDD to ground, right? Because there's no perturbation in VDD, so that is what we are doing with this part, which is what we call is at also AC ground, right? So this is what we call it as a AC ground, right? And similarly, we see that for the current sources, this would be open circuit. So now if we were to calculate, we want to calculate VDS, right? So this is what we want to calculate. How do we calculate VDS? So we see how much is the current flowing through these resistances. So now here, if we see, we can make this like this. So there is a GM VGS, which is the small VGS, right? This is source is grounded here. Source is grounded. This is a GM, which is where you are applying this V in, right? You get as a response of it, you get this current, which is GM small VGS. And as a response, you also get R naught of this because of the current channel and modulation. And then we have RD also, which is coming in parallel to this, right? So this is your V naught. So now the V naught, if I were to calculate, what is the V naught? V naught is the current flowing through this equivalent resistance, right? This equivalent resistance is So we can write this as, because they both are in parallel, so we can write as R naught parallel RD, right? So the current which is flowing through this, because there is no current going out, right? Because it is an open circuit. So we see the current flowing through this has to be GM VGS. So then the V out, which would be minus GM, sorry, the current which is flowing, which is GM VGS. And what is the resistance? Which is R naught parallel RD, right? From there, if we put VGS, we know it's V in. So then we can say that the V naught divided by V in is nothing is GM R naught parallel, right? So if you do the GM calculation, you will see this also comes same as this, because this is nothing. This is your also GM RD, right? In this we have, so why we have neglected? So if, because we know that for a very low lambda, R naught is much greater than RD, then this can be also seen as that V naught divided by V in becomes minus GM RD, which is what we got through the DC analysis. So that is the one thing which you have to see, that using the simple analysis of perturbation or the small signal model, you get the same result what we were looking for in the full IV analysis, right? So I think this is enough. If you want me to solve, this can be also solved easily. Here we see that we again say that assume no perturbation in I1. So that means this would be open circuit, right? If there is no perturbation, this would be open circuit. And then what we are left with, drain, so gate, source, drain, source is grounded, gate we are applying VGS, which is V in. There is a current which is flowing as a result between, which is GM VGS, and we have the R naught. That is all. We don't have any external bias because this is infinite impedance, right? If this current source. So that means this V naught, now we know that the GM VGS is flowing through this. So V out would be equal to minus GM VGS into R naught, right? And VGS we know it's V in. So this is V in into R naught. This is why gain would be V naught divided by V in would be minus GM, right? So this is how you can easily apply, and this also the same way you can go ahead, and now you have to make two small signal, right? So this is, you will see that this is easy to make for you, right? So let's, this is G1, this is your S1, this is your D1, right? D1 for this, and where you see that you are applying a small V in, and you get the response of it, you get your GMV in, and there is a R naught 1. This is to this node. Similarly, for M2, you can make another small signal where we discussed, again, you can say this is S2, this is G2, this is T2, because it's a small signal. So we can say that there is a VGS, and as a result of it, there is a current which is GM VGS, and there is a resistance which is R. And now you have to merge, because D1 and D2 and G2, they are merged. So G1 and G2, this will merge, right? So this is because of the this shorting. And when we see this is shorted, and if you now do the D1, so now I'm just bringing it here. So then you see what would be on the other side. So this is in pair series, S1 and S2, because S2 is also shorted, AC ground, right? This is anyway shorted. So S2 is also shorted to this. This becomes GM VGS, GM2, sorry. Let's call it 2 so that you know. And VGS, VG2. Now VG2 is this VGS. So let's call it VGS2 so that it's very clear. VGS2, right? And this part you see, now we are, okay. So there's R naught, and then there is a part of this. This VGS2 is nothing. It's basically your V out, right? So from this analysis, now you would be able to see that in R naught and R naught 2, how much current is flowing, right? So this is the sum of these two. So then we can see clearly that what is our V out by V in. You can calculate from this network. Okay.